Hi, and welcome to Tom Kennedy Science, and I'm your host, Dr. Tom Kennedy. Today, I want to talk about how the Earth's climate has changed throughout its long history, and it has changed quite a bit. And this is important. It's really important to understand how the Earth's climate has changed, what's caused it to change, and what the implications of that mean, because this is, of course, a series on climate change and why it matters. And it's important with understanding how it's changed in the past, because by understanding how the climate has changed in the past and the implications of it changing in the past, then guess what? We can understand how we're changing it today and what's going to happen when we change the climate. So, hey, there's this thing we got from the geologist. Thank you, Lyle, from Principles of Geology. Wow, was that like back in the 1800s? You influenced Darwin and you still continue to influence us today. But uniformitarianism, uniform means the same. Understanding the past is a key to understanding the future. And of course, we expand that to mean is that the way that nature works in the past, present, and the future, and everywhere in the universe is basically the same. So yeah, understanding the past is key to understand the future. You know, when the Earth was young, the Earth is about 4.6 billion years old. And when it was young, in its first billion or so years, let's go back to the Archean, the sun was actually fainter than it is today. And in fact, it was only about 75% as bright. Yet, if you go back to the Archean 3.8 billion years ago, the Earth was covered in an ocean, or at least all the rocks we find were mostly in water. So there was liquid water. So despite a fainter sun, the Earth was still warm. Why is that? And the reason why we think that the Earth was so much warm, greenhouse gases. There was a lot of methane and carbon dioxide in the atmosphere, which acted as a blanket keeping heat in. And of course, water as well. Water is also a very important greenhouse gas. So the greenhouse effect has been important for the Earth's history and the evolution of life for billions of years. Now, the Archean ended about 2.5 billion years ago. We entered what is called the Proterozoic Eon, and that lasted from about 2.5 billion years ago to about 542 million years ago. Now, during the Proterozoic Eon, sometime around 700 to 600 million years ago, it's been hypothesized, based on evidence, that the Earth was a snowball. Yeah, it's called the Snowball Earth hypothesis. That there may have been ice sheets covering the Earth all the way down to the equator, and that the large parts of the ocean were frozen over. So we call this a Snowball Earth. Now, what would cause the Earth to cool off so drastically? Well, there's lots of reasons why. One is we think that the continents moved to the equator, to equatorial regions. And this is important because there would be a lot of rain, a lot of rock weathering, and with a lot of rock weathering and rain, what would happen is that would react with carbon dioxide in the atmosphere and actually lower CO2 levels, causing the climate to cool, all right? And then if you cool, you get more ice. Ice reflects sunlight, so an increased albedo, so you absorb less energy. And then as you continually cool, you get this positive feedback loop. Hey, it's a little bit cooler this winter, not as cool this summer. You melt less ice. You reflect more heat back into space. You go into winter with a little bit more ice, and you can see that you have this positive feedback where the ice continually grows until it completely encapsulates the entire Earth, and it's called the Snowball Earth. And it's a pretty interesting hypothesis. And the reason why we think we're able to break this 100 million year long ice age is that volcanic activity continued throughout this entire period. And volcanism adds carbon dioxide to the atmosphere. So over time, enough carbon dioxide was able to build back up, warm the planet, and melt the ice. Now, of course, the Snowball Earth always reminds me of Ice Planet Hoth from The Empire Strikes Back, where there's hidden rebel bases. I'm sorry, I can't help myself. Got to make the Star Wars references when I can. Now let's jump ahead. We're going from 600 million years ago to 350 million years ago in a time period known as the Carboniferous Period. Now, we've changed eons. We're no longer in the Proterozoic. We're in the Phanerozoic eon, which lasted from 542 million years ago till today. And then the first era, and all these eras and eons, is a Paleozoic, which just means old life. And of course, a Carboniferous was 350 million years ago, named after the large coal deposits that it left behind. Now, this was a period where the Earth was really warm, wet, and swampy. There was no ice at the poles. Carbon dioxide levels were like 2,000 parts per million in the atmosphere, much higher than today, about 5 times higher. So the Earth was like in a hothouse. Now, over time, the Carboniferous ended and the Earth actually cooled. You see, with all that photosynthesis taking place, plants were removing carbon dioxide out of the atmosphere and it got sequestered. It got lithified. Litho means rock. So it got lithified as coal deposits. So we're mining coal from over 300 million years ago, releasing that carbon dioxide back in the atmosphere. But the activities of plants over like 50 million years lowered CO2 levels so much that the Earth went into a small ice age and cooled off to a temperature that's more like today. Now, about 252 million years ago, we saw an end to the Paleozoic Era. And that end was marked by a mass extinction caused by intense volcanism in an area known as the Siberian Traps. And this is one of the greatest mass extinctions. And this massive amount of volcanism did two things to the climate. First, it rapidly cooled temperatures. And the reason why it rapidly cooled temperatures is because all this volcanism was just spewing material up into the atmosphere. And intense volcanism will spew all kinds of sulfates and particulate matter into the atmosphere and cool the planet quickly. But these volcanoes did not stop, and they continued to put out carbon dioxide and other greenhouse gases. So the Earth's temperature dipped and then rose over millions of years, causing one of the greatest mass extinctions in Earth's history. And then we went into the Mesozoic Era, which, as you know, it's the age of the dinosaurs. And the Mesozoic Era ended with a bang, literally with a bang. 65.5 million years ago, a large meteor impacted the Earth. And of course, that affected the climate on day one, right? It spewed up immense amounts of ash into the atmosphere, caused global fires, a giant tsunami went around the planet, and temperatures cooled, and it wiped out about 50% of all life on the planet. And of course, we have great evidence for this. We have an iridium layer. Iridium is an element that's pretty uncommon on Earth, much more common on meteors. And we have this layer of iridium around the Earth right at 65.5 million years ago. And of course, dinosaur bones are below that layer, but not above it, showing the mass extinction event. And of course, this is the crater, the Chicxulub crater off of the Yucatan Peninsula, right off of Mexico. And there's even fossil beds in North America that show like this giant tsunami that took sea creatures and threw them on land. So you've got a fossil bed of like sea creatures mixed with land creatures. It's amazing. But that started our current era, the one that we're in, called the Cenozoic. Now, the Cenozoic, for the last 65 million years, we've seen a gradual cooling of the planet. And there are several reasons for this. I'm showing you a picture of the continents. One is, you can see that South America, Antarctica, and Australia are down there kind of together, but that's going to change. The movement of the continents is starting to change here. By about 35 million years ago, Antarctica totally separated from South America and Australia, and you develop these currents going around it, which isolated it from the rest of the world, and Antarctica froze over. 35 million years ago, there were forests on Antarctica. It was forested. It had amphibians. It had birds. It had entire ecosystems down there. Now it's just covered in ice. But this was the Earth beginning to enter some ice ages. And the reason why this cooled off, we believe, it separated from South America and Australia, causing changes and global circulation of the oceans. And global circulation is how we transport heat from the tropics to the poles. So it became isolated and got really cold down there. Now let's jump ahead to about 2.8 million years ago. Up until this point, Central America and South America were isolated. And once again, global circulation patterns are moving and distributing heat, moving heat to more northern parts of the world. Well, about 2.8 billion years ago, South America and Central America became connected when the Isthmus of Panama rose. And what that did is it connected North America and South America, but it also altered global circulation patterns, and the Earth began to rapidly cool, and we entered into a full-blown ice age about 2.6 million years ago, known as the Pleistocene. And we are still in an ice age today because we have permanent ice on both poles of the planet. Now, for the last 2.6 million years, this ice age, we've had glaciation. We've had ice sheets all the way down to Kentucky. We've had periods of the Earth where the water level was over 300 feet lower than today. Now, one thing that's interesting about these ice sheets in terms of they covering large parts of North America and Europe, and this map is nice, but it doesn't show like the drop in sea levels. Florida had been much larger back in those days. But one of the things we also learned is that these ice sheets ebbed and flowed. We had periods of maximum glaciation as shown here, interspersed with interglacials, which is what we're in now. And that was caused by changes in the Earth's orbit called the Milankovitch cycles, which changed the solar radiation coming into the planet, which affected carbon dioxide levels, and of course affected the amount of ice on the planet in terms of its climate. So here's some interesting things that we've learned by looking in the past. We know that the climate has changed in the past. That is incredibly true, and we see fantastic evidence of it. We've had warm periods, we've had cold periods. One thing that we learned, this is incredibly important, the composition of gases in our atmosphere matter, and they matter a lot. The amount of greenhouse gases like carbon dioxide, methane, and even water, these things warm the planet. So the more methane, the more carbon dioxide you have on the atmosphere, the warmer the climate is going to be. And you can see that based on the chart and how that CO2 levels have changed throughout time. So today, we know that carbon dioxide levels are 415, almost 420 parts per million, higher than it's been in millions and millions of years. And this is important because when CO2 levels are high, the Earth is warmer, there's less ice, sea levels are higher. That's what sea levels look like. The last time the Earth was about 2 degrees warmer Celsius, about 3.8 Fahrenheit. Sea levels were nearly 20 feet higher, and we're already past this point. So we're kind of locked into this much climate change and sea level rise, potentially. Yeah, that's going to cause a lot of economic damage worldwide. Another thing that we've noticed with past climate change that's really important, mass extinctions. And in fact, we've had the big 5 mass extinctions. We are almost certainly in a mass extinction today. And one of the worst mass extinctions, of course, was the Permian, where I told you it was like that 1-2. You had rapid cooling followed by warming. So you had 2 waves of extinctions that led to over 90% of all life in the oceans and probably 60 to 70% of all life on land dying. And it did it relatively quickly, probably within 100,000 years or so, which, hey, on geological timescales, that's a blink of an eye. So, as we reconstruct the Earth's past, higher CO2 levels, we have warmer climates, lower CO2 levels, we have cooler climates. So then we need to understand, okay, what's affecting CO2 levels in the atmosphere? And we know that there are natural ways to affect it. Position of the continents, the position of mountains. Are you mountain building? One of the things recently is that as the Rocky Mountains have risen, that's doing some rock weathering. That's lowering CO2. Position of the continents can also affect global circulation models as well. Over tens of millions of years, billions actually, changes in solar output matter. And they also matter on short time scales too, but not to see drastic climate change. Of course, meteors can cause rapid climate change, as we saw with the end of the Mesozoic Era and the end of the dinosaurs. Periods of intense volcanism can also rise temperatures. And of course, for the last 2.6 million years that we've been in the last ice age, the Milankovitch cycles, which are changes in the Earth's orbit and tilt over time, also affect these periods of maximum glaciation and interglacials. Okay, so that is an incredibly brief synopsis of climate change over the Earth's history and some of the things that affected our climate change and the implications of that. Well, stay tuned for my next episode. We start talking about the evidence for modern day climate change. Till next time,